That's all SSH needs from you. This actually seems to work, which, is a nice thing, actually. Now, SSH does have another system called Bubble Babble, which attempts to wrap, and it actually got brought up here. Someone asked me about it. It attempts to map names to syllabic sequences, like Zigaz, Tosus, Vusik, Masar, whatever. The problem is we're not really built to remember arbitrary sequences of syllables either. That's just not what we do. However, gotta actually admit, names are fairly arbitrary. Boutros Ghali is a fairly arbitrary name. Maybe we can merge the approaches. Zigos and Tosik Visuk, Masar and Sivik Siled. It might work. I think it requires testing, but we'll see. I'm actually going to try to get some tests done. So, we could actually invert the flow. Check this out. How many people here have passwords that suck? They're like lowercase hell, $3, tilde, you actually speak this thing out like that one up there, that's 23 syllables. What if you just type Dirk and Kuk Kolapajlo and Omar and Gina Heimel? A, you actually get more entropy, 64 instead of 48 bits. B, it's less syllables to communicate, sounds better on a phone, and oh, by the way, how nice would it be to have spell check for your password? I'm just saying. So I'm actually working on this too, and that would actually be dear God, that would save me some annoyance. So I'm working on this, I call them passnyms. So it's easier to interface with systems when symbols align. Hacking is just another form of interfacing. So we're going to move on to the next section of this talk, which talks about fuzzing. We can really break stuff with garbage syllables. It's depressing. You take some file, you flip 10% of the bits randomly, and everything blows up. It's a lot easier than code review. It sucks. So it's very dumb, though. You only end up catching small little chunks. Now, we can break things way more than dumb fuzzing, which already breaks too much, if we actually, know what the hell we're doing. That's what we call smart fuzzing. We take a file, we understand its internal structure, we fuzz that structure, which we understand, and we see what happens. Someone was showing me a really cool PHP fuzzer earlier. Dumb fuzzing is really easy. Smart fuzzing is very labor intensive. It requires smart people and specifications. Well, wouldn't it be nice if we could automatically discover what symbols a computer parser was trying to see, to understand? Well, file formats are languages. Who here took a linguistics class ever, studied some language design? Okay, guys, seriously, language is fun. I know it's shocking, but it really is. Kids don't actually get the docs to English. I wouldn't want to see them if they were written. Kids don't get the documentation. They just pick them up just by watching lots and lots and lots of samples. Now, they can do this because they actually design all sorts of internal structure and redundancy into the language. And I mean they, as in the kids. Children are the actual progenitors of language. They actually create it. Adults, two cultures merge, and they just sort of oh crap, we've got to talk to each other, and they make this horribly sounding stuff called a pidgin language. It's like a working language. And then the kids hear and go, oh God, this is terrible, and then they do something good. Well, children make languages. Adults make working languages. Programmers make barely working languages. Hell, no one actually has to read this, so we can just go buck wild. And they do. But there's still quite a bit of internal redundancy to these languages. Let's see if we can auto-discover the redundant content. So, there's this great piece of code called Sequitur. It's a linear time pattern finder. It creates what are called context-free grammars from arbitrary input. And when I mean arbitrary input, it's linear time. You can pass hundreds of megs of data into this thing. It'll be like pattern, 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 and it won't slow down no matter how much you throw at it. This is cool. Anyone here ever find a really cool and awesome algorithm and go, wait a second, if I give it more than 100 things, I'm going to be here all day. Sequitur's linear time. Basic thing that it ends up doing, it would take the input C of switch C, case 1 value 2, case 2 value 3, case 3 value 4. It's like a compression algorithm. It figures out, case is a symbol and value is a symbol. So I'm going to turn those into A and B. And now my message is going to be switch C, A1, B2, A2, B3, A3, B4, A4, B5. This was created by Craig Neville Manning as his PhD thesis like a decade ago, and he's kind of sort of the chief research scientist at Google. I guess I'll do the evil. So one of the things I started doing, because hex really does suck. It sucks so bad that like fixing it, there's a really low bar. Anything is better. What I did is I said, to reconstruct this message right here, you have to go a certain number of hops in and into the grammar. Like for case and value, you have to get out of S and go one level into A. And A could have B and B could have C, and then C you might have to go another level, another level. Well, how many levels do you have to go to reconstruct each byte? I figured I'd draw it, see what it looks like, visualize it. And what I ended up finding, you can't at all see it in this view, but you see I've given this talk, at least this thing before, so I've seen that it wasn't visible. Much better. Sequitur's finding the internal structure. These are actually hex bytes that I blurred and zoomed in. And immediately, you run this code, and Sequitur's like, oh, here's all the patterns. Let's look at what it's actually finding. I actually went into the output of Sequitur and figured out what symbols it was finding. And it's like, hey, look, we got symbol 84, literal D6. Symbol 84, literal EE. Symbol 84, OC. Now we're on symbol 85, 28. Repeated sequence, single byte literal. Repeated sequence, single byte literal. This is just extracted from the data. There is no like manual operation of, oh, I see this, I see that. No, it just showed up. My goal here is to build better first knives for going after new protocols, and that's pretty cool because I wouldn't want to have to come up with that off the top of my head. And I think there's actually a fixed distance between some of these, like A6, B6, CC, and so on. So we can get even more fun here. For various definitions of fun. Let's start drawing links in between the symbols as they are expressed. Now let's say we just took letters. S leads to W, W leads to I leads to T, T leads to C. That's just going to be a mess. You're going to have like the T leading to the C in switch and like the space leading to the C in case, and it's just going to be a big meaningless mess that has no bearing on what a C compiler parser is trying to do. It's carbonated? Okay. But now, let's look what happens when we actually draw together all the symbol flow with Sequitur. Switch C leads to case, which either leads to 1, 2, 3, or 4, which always leads back to value, which either leads back to 2, 3, 4, in which case it will always go back to case, or value is going to go to 5, in which case it terminates the call. That is actually an accurate view of what the parser's up to. And this is completely extracted from nothing but samples of the data. That's cool. That's a completely new domain that we can go mess with, because we can totally fuzz that. So I built a new tool. It's called the CFG 9000. All right. Time's right now? All right, cool. Rock. It reduces input data into a stream of symbols. And now once we got symbols, let's go fuzz those. Just like we were going to do with bytes with a dumb fuzzer. We can shuffle them around, we can drop them, we can repeat them, we can corrupt the symbols, but do it in a way that is consistent. Every instance of this symbol is broken. Rock! Now, Sequitur is not necessarily the best way to generate a grammar. Doesn't handle recursion, which, by the way, this is hugely used in bioinformatics. And the genome is, now that's a language, dear God. There's another approach called suffix trees that may yield better output, but Sequitur scales, like a lot. Like everything else is not linear. Sequitur will take gigs and like just sort of take up all your memory. So some sample output. I ran it on, I had Sequitur fuzz itself, and so calculate rule usage. Oh wait, this is a simple calculate rule usage, and so on. I ran this on HTML, and we actually got valid HTML, sort of, and certainly more meaningful symbols than if I had just flipped arbitrary bits. And here's another example. I'm not sure what it's doing, but the browser took it. Now, this is not the best context-free grammar fuzzing ever. Great quote. Many physicists would agree that had it not been for congestion control, the evaluation of web browsers might never have occurred. In fact, few hackers worldwide would disagree with the essential unification of voice over IP and public-private key pair. In order to solve this riddle, we confirmed that SMPs can be made stochastic, cacheable, and interposable. This means nothing. But it got accepted as a paper at a conference. Context-free grammars are pretty cool. They basically fuzz the con and won. So what my goal is to be able to create something that could just look at a whole bunch of papers, or look at a whole bunch of JPEGs, or look at a whole bunch of things, and create something that is semantically meaningless and, in fact, broken and corrupt. But at first glance, maybe even at 10th glance, hey, that's valid. Sure. Why would physicists disagree? And we'll skip this slide, actually. So I've been working on an updated version of Sequitur called Requitur, which is optimized for fuzzer use, generates larger symbols, eliminates redundant symbols, maybe remove the in-memory grammar requirements so we can scale up to, tens of gigs, grab all symbols from your hard drive, and, add foreign grammar capabilities so you can start analyzing files relative to everything else. But what do I got now? Oh, by the way, code release, ho ho kiddo, 2006. All this stuff is actually, it's crap, it's out. And yeah, if you're trying to figure out how to use it, please send me an email. Maybe I'll figure it out by the time I get it. So Requitur is actually 8-bit clean, which Sequitur isn't. You can't really use Sequitur to analyze raw binaries. Sequitur's been fixed to make that happen. And I created something called merge.dot that actually outputs the graphs that I showed you earlier. So how to think of Sequitur? This is what I want you guys, because there's so much awesome work that can be done here now that we have a symbol-level view of all the data we ever look at. Instead of thinking about bytes, think of arbitrary symbols that can be any length, but they're just units. Every time you're thinking, oh, let's look at trigrams, think, instead of bytes, symbols. Instead of Bayesian probabilities for characters, I wonder which character follows which character. Think what symbol follows what other symbol, because that's going to give you the actual flows through the applications that you're trying to break. If you adapt yourself to more than 256 codes per symbol, you're going to be well rewarded for the effort. And if your code's already Unicode aware, you might already be one step ahead. So, symbol analysis systems do kind of have a problem. Languages, kind of like synonyms and more than one way to say it kind of deals. And very similar messages can be encapsulated in very different ways. Very similar messages can be encapsulated in almost identical ways, but they'll still show up as different symbols because the raw bytes are different. This is actually a fundamental weakness of Sequitur. It's looking for exact matches. We need ways of fuzzily linking together our grammars. Now, there are some things we can do by taking all of the entities that our grammar generators come up with and saying which symbols are really close to each other, and then starting to do fuzzing where you do, fuzzy match fuzzing. Somehow that works. I'm going to replace this with a symbol that is similar but non-identical. That sort of stuff. That could be done. But we need to have ways of analyzing, perhaps visualizing, similar but unequal systems. Because the things we're trying to break have a lot of similar but unequal properties. So there's another approach. It's called dot plots. Dot plots are cool. They're pretty. A popular mechanism for visual analysis of human genome, of genetic data. Now, there have been some attempts to apply dot plots outside the domain of bioinformatics. Fair amount of textual analysis, actually some audio, which is how I had heard of it. One of my hobbies is actually audio compression. And there was this really cool old paper called Visualizing Music and Audio Using Self-Similarity. And what it did is it split a song into these little tiny chunks, and it said, I'm going to take each chunk and tell you if it sounds like each other chunk. And I'm going to put it all on a graph. And there's actually a tool you can get from Linux called Disassociated Studio that'll do this for you. And this is actually a Beatles track that they did. And they showed, hey, look. This section right here has this one pattern. This section looks visually different. That section looks visually different. That section looks visually different. As they went through the various segments of the song, very different visual patterns actually erupted from the data. Cool. What if we do this on an MPEG? Way better data. Whoa. That was pretty much my reaction when I was first playing with dot plots. Like, wait a second, this actually works? But yeah, you actually end up getting way more data about what's going on inside a file. So what exactly is going on here? Jonathan Hellman wrote this great paper called Dot Plot Patterns, a literal look at pattern languages. And this was his example. Take Shakespeare, to be or not to be. If we put